Okay, so finally we are going to study integration. So this is chapter 11. This is the last chapter of this first volume. In the previous chapter we discussed differentiation. Now by integration we actually mean, more specifically mean, the definite integral as opposed to the indefinite integral which is also known as the antiderivative. In fact, it's not that you do not know these things. You already know these things from calculus. And these two notions, that of the definite integral and the antiderivative, are linked by the fundamental theorem of calculus. There are in fact two fundamental theorems of calculus, and we are going to discuss about them towards the end of this chapter. Alright, so now what are we going to see here? Say I is an interval in the set of real numbers, and suppose we have a function f which of course is real valued. This is the kind of function we are discussing, and it has I as its domain. So what we want to do, we want to attach a number to this function which will be called the integral of this function over the domain I, and that number we will denote like this. The integral, this is the integral sign which is elongated S, elongated capital S, followed by f, and here you write I, the interval over which we are going to do integration. Now this notation may look somewhat incomplete. In its place, actually this is also a valid notation, but in its place you can write another notation, say something like this, showing the variable and dx. Yeah, now it looks more like what you have already seen in calculus, but still it looks somewhat not like what you have seen in calculus. In fact, if this interval I has endpoints, if it has endpoints means of course it will have endpoints, and if those endpoints are a and b, say the left endpoint of I is a and its right endpoint is b. In that case, instead of these two notations, we can also denote the integral like this, or like this. And now this one really looks like what you have seen in calculus when you do definite integration. Now there may be a question in our mind which is just this: what is this dx? What is the reason for having the notation like this? We do understand that we somehow have to indicate that we are calculating the integral of f. So for that we have a sign which denotes integration. Fine. We also somehow need to indicate the interval over which we are doing integration. So here you have I, or you can indicate that by writing A and B. Okay, A is the left endpoint of your interval and B is the right endpoint. Fine, and you are integrating f, so of course f has to be there. So f of x, but what is this dx? Okay, this question arises every now and then in our minds. Many times it may have arisen while doing calculus. What is this dx doing? What is its purpose? This will be understood to some extent towards the end of this chapter. Okay, when we study an extension of one of the two ways of integrating a function, then we will realize why we have a dx here. But the actual reason, the actual meaning of this dx, that will not be found in this text. For that, we have to see differential geometry. But anyway, so now we have this thing. Now there is one more thing that I should point out. Here, this is something you already know, but let's again see it. Here, x is a dummy variable, which means that in place of x you can use some other letter also, nothing will change. For example, if in place of x you write say y, then this and this mean precisely the same integral, the same number. Alright. Now it turns out that the task of defining this integral is a little delicate. Okay. And there are at least two distinct ways of doing this. At least two. That means there are more, actually there are more. Okay, we are going to discuss only two of the most popular ways of integrating functions, but there are others also. The one which we will first consider is the Riemann integral, named after the German mathematician Bernhard Riemann. Georg Riemann, actually the name is long. Riemann was a student of Carl Friedrich Gauss actually, and his name is also linked with a very famous unsolved problem in mathematics known as the Riemann hypothesis. It is still unsolved, although very recently there has been a little progress on that, just a slight progress, a significant progress, but only a little one. So let me just also write the time period, because that's how we address them. To 20th July of 1866. Very short lives they had. Okay, this kind of persons should live longer. And the other way is Liebig integration. named after the mathematician Henry Liebig. It's pronounced Liebig, okay, although you have S and U here. Henry Leon Liebig, I think, I don't remember exactly. 28th June 1875 to 26th July 1941. I am very bad at remembering these dates and all. Okay. Now it turns out that the Riemann integral is okay for a very large class of functions. You can integrate a large class of functions. A large class of functions means you can integrate all the functions in that class using the Riemann integration technique. But still there are some functions which are not Riemann integrable. They can be handled by the Liebig integral. This is a superior integration technique which supersedes the Riemann integral. That means using the Liebig integration technique you can integrate a far larger class than the class of Riemann integrable functions. The relationship between these two is somewhat like, this is a very vague analogy, okay, like the relationship between the Newton's laws of gravitation and Einstein's general theory of relativity. If you have an object, you want to know how the object moves. If the object is neither very large nor very small, nor is moving at a very high speed, then Newton's laws of gravitation, Newton's laws of mechanics, they are going to tell you what is going to happen, and that's a very good approximation to the reality. Reality means really how the object moves. However, if the object, for example, becomes extremely small, then its dynamics is no longer classical, it starts to become quantum. If it is extremely large, then also Newton's laws break down. There you have to apply general theory of relativity. If it moves extremely fast, you have to apply special theory of relativity. So something like that. There are cases, important functions which are not Riemann integrable but Liebig integrable. And also there are functions which are not integrable at all. So we are going to first of all see the theory of Riemann integral. This entire chapter is about Riemann integral, not this one. This one we are going to see in the second volume of Tau's analysis. And that is in fact the last chapter there also. But in this chapter itself, we are going to see an extension of the Riemann integral, known as the Riemann Stieltjes integral. It's pronounced Stieltjes. This extension was devised by Thomas Stieltjes. And the time period for this mathematician is 29th December 1856 to 31st December 1894. Oh, I thought 1984. I was going to write 1984. This Dutch mathematician Thomas Tilges, he made many contributions to many different parts of analysis, especially some things called moment problems and continued fraction. Continued fractions are studied towards the end of, I am saying about a text that I am following, Barton's elementary number theory. So their continued fractions will appear towards the end. Okay, it's a large area. Now, how exactly are we going to introduce the Riemann integral? It is usually introduced using the notions of upper and lower Riemann sums. Upper Riemann sums and lower Riemann sums. That's how, using these notions, the Riemann integral is usually introduced, that means defined. Oh, and one more thing, the pronunciation here is not Riemann, it's Riemann, okay. But in this text, this is not how the integral will be introduced. Although we will see, these things also will come, but that's not how we are going to define the integral. Here the strategy is something else. Here we are first going to consider a class of very simple functions. In this class you have piecewise constant functions. Perhaps the name itself tells you what these functions are. These functions are functions which are not exactly constant. That's not necessarily true. All the constant functions are also piecewise constant. But the thing here is that, say you have a function defined on an interval I. Say I looks like this. Okay. So this is A, this is B. For specificity, let's consider this closed interval A comma B. So what you do, you subdivide the interval into small subintervals. In each subinterval, your function is constant. That kind of functions are called piecewise constant. So the graph literally will look like this. In a given subinterval, the value is constant. In another subinterval, that value may change, but in that subinterval, it is still constant. The advantage of considering this class is that it's extremely easy to integrate these functions. Now, all of us who have come to this stage already know from calculus what integration is and how it is related to areas under curve. Okay. So you may already see why such functions are very easy to integrate. But we are not going to talk about areas or any such geometric things. We are not going to use geometry to define integration, because that's not how we are proceeding in this text. We do not use the axioms of geometry. Geometry is something which helps us visualize the things, but we instead use set theory, the number systems, the things that we have developed rigorously, not geometry. And we are going to use the properties of the real number system itself to define Riemann integration. Okay, now the strategy here is this. You consider this class of functions, piecewise constant functions. You develop a theory of integrating them, okay, and a very elementary theory of integrating them, and then using that theory you move on to more general functions, their integration. Now, before we can consider piecewise constant functions and the definition of their Riemann integral, we need to know about partitions. How we can subdivide a given interval into smaller subintervals. In other words, how we can partition a given interval, that we need to know. And throughout this chapter, all intervals are bounded intervals. Now, if one goes back to the definition of intervals itself, which is definition 911, well, is it the definition of an interval or the definition of, I think it's the definition of an interval. I don't think it's the definition of a bounded set. But anyway, what I want to say here is that if you go back to the definition of intervals itself, how have we defined intervals? Actually, we have defined intervals not just in the real number system, but in the extended real number system. What is that? You already know that the extended real number system consists of all the real numbers, and along with that these two extra objects, plus and minus infinity. If you remember, we successfully extended the ordered relation that we have on R to this entire enlarged system, R star. And it turns out that that extended order has all the properties that the ordinary order on R has. Okay, and using that extended order relation, we defined intervals in R star itself like this. Suppose you have two extended real numbers A and B. Then the closed interval A comma B, for example, has been defined to be the set of all extended real numbers x such that these inequalities are true. A is less than or equal to x and x is less than or equal to b. This interval may or may not contain these infinite extended real numbers. It may actually be a subset of R itself, or it may even be empty. All of these things depend entirely on what A and B themselves are. Now, by a bounded interval, we mean that A and B are real numbers. Okay, that's what we mean. So this is it's not a definition that has been considered again here in this chapter, but let me just write like this. Just for our own sake, a kind of a definition. Let A and B be real numbers such that A is less than or equal to B. Then the intervals closed interval a comma b, closed open interval a comma b, open closed interval a comma b, and open interval a comma b are called bounded intervals. Okay. So when we say that an interval is a bounded interval, we mean this. And this is the kind of intervals we are going to consider throughout this chapter. And that means, in particular, we will not consider this, for example. Okay, this is not a bounded interval because the right endpoint of this interval is not a real number. It's this extended real number. All right. Now, before we see partitions though, we need to define something else, namely the notion of connectedness. And this is the actual definition, the first item of this section, 11.1.1. Let X be a subset of R, any subset of R. We say that X is connected if for any two elements. Keep in mind that X is a subset of R. So the elements in X are, after all, real numbers. For any elements X and Y in X, satisfying this inequality that X is less than Y, we have this. The closed interval X comma Y is a subset of X. If this happens for any two elements X and Y in X, then we say that X is connected. We need this primarily in order to state and prove a result which lets us very quickly see when a given set is a bounded interval. Okay, that's why we need connectedness. We will realize what that means very soon. And there is a remark after this, right after this definition. And the remark is basically this. We are also going to see this notion of connectedness more generally defined for metric spaces in the second volume, in analysis 2. Now let us see some examples. The set closed interval 1 comma 2 is connected. Let's see how. So that means if we simply apply the definition, we need to consider two elements X and Y in 1 comma 2 such that X is less than Y. Our aim is to show that the closed interval X comma Y is contained in 1 comma 2. That means you need to show that the closed interval is a subset of this. So you take any element in the closed interval, let z belong to x comma y. Then x is less than or equal to z and z is less than or equal to y. That's what being in that closed interval means. Now since x and y themselves belong to 1 comma 2, we have two inequalities. Y needs to be less than or equal to 2 and x needs to be greater than or equal to 1. Of course, x will also be less than or equal to 2 and y will be greater than or equal to 1, but we need these two specific inequalities. Because if you combine this with this, then you get the inequality that z is less than or equal to 2. And combining this one with the first one, you get the inequality that 1 is less than or equal to z. But then 1 is less than or equal to z and z is less than or equal to 2. That is this. Okay. So any element in that interval is also here. So this is a subset of 1 comma 2. And that's how 1 comma 2 is connected. Similarly, you do understand the reason for choosing this word connected, right? Like you imagine geometrically this set on the real line. It represents the line segment which is not broken into pieces. It is in one piece. That's why it is connected. Similarly, following a similar argument, you also have that this open interval is connected. But not all sets are connected. For example, this set is not connected. Union 3, 4 is not connected. Why? What is the reason? Note that two and 3 both belong to this set. Specifically 2 belongs to this part and 3 belongs to that part. But the closed interval 2, 3 is not a subset of the given set. And 2 of course is less than 3, that need not be mentioned separately, it's known. This is not a subset of this. And why is that so? For example, 2.5, the middle point of this interval is an element in this interval which is not present here. Okay, and that is why this is not connected. You can see that geometrically it is two disjoint line segments on the real line. So it's not connected. There is a gap. The real line is of course connected. Because you take any two elements x and y in R, say x is less than y, then the closed interval of course is again a subset of R. So R is connected, and geometrically you can see parallelly, okay. Geometrically R is connected because it is in one piece. But always keep in mind that when you think geometrically, never make that geometric thinking a part of your solution or your proof of some statement. No. You have to prove it analytically. The geometry will only help you in understanding what you are trying to get there. Okay. So it's for that purpose. But there are some other somewhat silly connected sets which are connected for trivial reasons. Any singleton set where R is a real number is connected, because the condition for connectedness for this set is vacuously true. Not going to elaborate what that means, you already know. Also, because of that same reason, the empty set is connected. Okay, now we state that lemma. It's because of that lemma only we have this notion of connectedness, that we need it here. So this is 11, 1, 4. Let x be any subset of R, then the following two statements about x are equivalent to each other. If one of them is true, then so is the other. X is bounded and connected. This is one statement. As a subset of R, X is bounded and connected. And the second statement is X is a bounded interval. Because of this equivalence, in order to prove that X is a bounded interval, it's enough to show that it is bounded and connected. So this becomes very convenient when later on we have to use intervals here and there, and that time we will have occasions to consider subsets of R such that we need to show that it's an interval, it's a bounded interval. Then this is how we show that it's a bounded interval. We show that it is bounded as well as connected. And its proof is the first exercise. So this we will handle in the exercise solutions. Okay. And there is a remark after this. Recall that because the above lemma says something about bounded intervals, right? So the author is reminding us of the fact that intervals can be degenerate also. Intervals can be singleton sets and also the empty set. The definition of intervals allows these things also to be intervals. Any singleton set, this is also an interval. In fact, the empty set is also an interval because these are not very complicated or very boring in a sense. So they are called degenerate intervals. A non-degenerate interval is an interval which is neither a singleton set nor the empty set. Now there is a very nice corollary to this lemma, and that corollary states that the intersection of any two bounded intervals is again a bounded interval. This is going to be very useful for us. Let I and j be two bounded intervals in R. Then the intersection is also a bounded interval. In R. And its proof is also going to be handled in an exercise. Actually, this is how this is a nice strategy for studying a section or a chapter. First, you study the things globally, and by globally I mean you proceed like this. You skip proofs entirely. You first see what the statements of the things are. You think about the statements. You see what the interrelations of the statements are, how one statement is related to other statements. So like that, you first do a global study, and then only you go to the individual proofs and understand them. That is the local study. If you combine these two types of studies, if you have time for all these things, then you will see that you have not only an idea of why each individual statement is true because you know its proof, but how the statements themselves are related to one another. Okay, that will create an overall image of the entire theory in your mind. An example illustrating this corollary . Say you consider, I won't write sentences here. You consider these two bounded intervals. Then their intersection is the singleton set 4, which is also a bounded interval. Similarly, the intersection of these two bounded intervals is empty because they are disjoint. There is no common real number. That is also a bounded interval. Both of these are degenerate, but after all they are bounded intervals, illustrating this corollary that the intersection of any two bounded intervals is also a bounded interval. Note one thing, that because this is a bounded interval, by that original lemma, it is going to be connected always. no matter what the situation is, you won't get the intersection of two bounded intervals something like this. Such disconnected sets will never appear as intersections of bounded intervals. Because they also have to be bounded intervals, they are going to be connected and of course bounded as well. Okay, and then next comes a very important notion, the length of a bounded interval. So this is a definition. Lengths of intervals. Let I be a bounded interval. Its length denoted like this is defined as follows. Now, depending on whether I is a degenerate interval or a non-degenerate interval, the definition is slightly different, although it's not unrelated totally. You will see what this is. If I is a degenerate interval, i.e., if I is either a singleton set or the empty set, then its length is defined to be 0. I is a singleton set or I is the empty set, then its length is defined to be equal to 0. Thinking of it geometrically also it makes sense, because if I is empty, well then it should have 0 length. But if I is singleton, then on the real line I is just a single point, and a single point has no length, should not have no length, and that's how we have defined it also. And next comes the case that I is non-degenerate. Next, let I be non-degenerate, i.e., I is a comma b closed interval or closed open interval a comma b or open closed interval a comma b or open interval a comma b, where a and b are real numbers and a is less than b. Okay, so I being not degenerate means I being of one of these 4 forms where the left endpoint is strictly less than the right endpoint. Then, so we have started like this, huh? Then the length of I can write here itself. The length of I in all of these 4 cases, no matter what form of interval I is, is defined to be equal to the number b minus a, and you understand why. So the next example will illustrate that. This is not the first time we have thought about lengths. You know that when considering length of an interval, we really think of the length as the length of that line segment on the real line which geometrically represents that interval, and that corresponds to b minus a. Example. The length of the closed interval 3, 5, for example, is 5 minus 3, which is 2, and the length of the open interval is also 5 minus 3, which is 2. If you go to degenerate intervals, for example this singleton set, then its length by definition is 0, and the length of the empty set is also 0. Okay, now finally we have come to the definition of partitions. Now we are going to define partitions. So this is item number 10. Partitions. The definition has many conditions. Okay, let us define it carefully. First of all, let I be a bounded interval. Well, the author could have not written bounded intervals also, because in the beginning of this section we said that all intervals that we consider in this chapter are going to be bounded intervals. So there is in fact no real need to keep on writing bounded, but he for some reason decided to do that. Maybe he thought we would forget that we are only considering bounded intervals. So anyway, he has written it like this: let I be a bounded interval. A partition P of I is a finite set. Each condition is going to be important. Okay, P is a finite set whose elements are themselves bounded intervals. Contained in I. That means P is a finite set consisting of some bounded intervals. The elements in P are not real numbers, but themselves bounded intervals and finite in number, and each such interval is contained in I as a subset. And each element of I is, or let me write like this, I lies in exactly one J in P. So the elements of P are bounded intervals which are all subsets of I, and if you take an arbitrary real number, a point from I, then that point lies in exactly one such element of P, exactly one such subinterval. We can call these elements of P subintervals of I, because first of all they themselves are intervals, and subinterval because each one of them is a subset of I. And in fact, to reiterate this point that the elements in P are not real numbers, there is this remark. Note that the elements in P are subsets of R. Intervals means subsets of R after all. And now examples actually we are going to consider a number of them. The first one this set. This is a partition of 1, 8. Let us verify. Okay. What are the conditions? First of all, P needs to be a finite set. Yes, it is. Because you can see that there are 6 elements in P. Then the elements of P need to be themselves bounded intervals. Are they? Yes. This is a bounded interval, an open interval, but after all bounded, because its left and right endpoints are real numbers. This is also a half open bounded interval, and so is this. And this 1 singleton, 5, and the empty set are degenerate bounded intervals, but after all bounded intervals. Are they all subsets of this? Yes. Each one of them is a subset of this. And then the last condition. If you take any x from this interval, that x lies in precisely one of these 6 sets. Okay. Now this condition actually tells us what? I mean, the condition expressed as such is a little difficult to verify, no? I mean, you take any x here and then you are going to see whether it belongs to at least one of these sets and then at most one of these sets. This condition ultimately is equivalent to two things. See, any x here has to belong to at least one of these sets means what? That if you take the union of all these sets, then that union should contain the given interval. The given interval is a subset of the unions of these elements of P. That is equivalent to saying that any element x here lies in at least one of them. But to lie in exactly one of them, you have to have all these things mutually disjoint. You take any two of these 6 intervals distinct to and take their intersection, that should be empty. So they should be mutually disjoint. So this last part of the definition, that each element of I lies in exactly 1j in P, is, instead of this, one could also say that I is equal to the union of the elements in P. So this is one condition, and the second condition is this. For any distinct J1 and J2 in P. So instead of looking at elements, if you think of these two conditions, then it will be easier to verify that P is a partition. Are these two conditions true here? You just imagine geometrically. Okay, you have the point 1, then after that you have the line segment 1, 3, where all the numbers lying between 1 and 3, they are common. But then you have from 3 to 5, you do not have 5, but you do have 3, and then the single point 5. Then all the numbers starting from the right hand side of 5 all the way up to 8, including 8. So yes, you are covering this fully, and that's why I is the union of all these intervals. And you can clearly see that the intervals are mutually disjoint. So the last condition is also true for this P, and that's why this is a partition of the given interval 1, 8. Now one may note that this is also a partition if from P you remove that empty set, which seems to be playing no purpose at all. It's just simply there, it's not doing any, it's not causing any problem, but also if you remove it, you still get a partition. As well. Now some non-examples, some collections of intervals which are not partitions. This one, for example, closed interval 1, 4 and closed interval 3, 5 is not a partition of 1, 5. You can see the reason, because, well, this is also a finite set, and both of these intervals are bounded intervals, and each one of them is a subset of this. But this condition has failed for this. These two are not disjoint. For example, 3 belongs to this as well as this. That is why it's not a partition. Another one, the collection of these two open intervals is not a partition of the open interval 1, 5. Well, it's not necessary that you have to take only closed intervals. This is also a bounded interval, but this is not a partition of this. Again, you see, this is a finite set, a finite collection of bounded intervals, each of which is a subset of the given interval. But this time, condition 1 has failed. Why? Because the union of these two intervals does not have 3 in it. This is not equal to the given interval 1, 5, but this. Okay, so this is also not a partition, this is also not a partition. And finally, you see, we have introduced 2 or 3 things today, but how are these things related to each other? Finally, we are going to state a result whose proof we want to see today. That proof, in fact, is not an exercise. It is there in the text itself, but that proof is big. Big means it's not exactly big, but there are many cases in the proof that we need to carefully go through each case. I am, however, going to state the result. It's an important result, and this result, it has a name also. Length is finitely additive. It's a result which is very natural. We feel that it should be true, but proving it is a different matter. And with this statement, we are going to end today. Length is finitely additive. Let I be a, see again here, bounded interval. We could, if we want, we could simply write let I be an interval, because we have already agreed in the beginning itself that we will consider only bounded intervals. And let P be a partition of I. Actually, you could simply write till this, but the author has additionally written let P be a partition of I of cardinality n. There is no need to keep this of cardinality n part in this statement itself, but the proof of what we are going to say next involves induction on this cardinality. So for some reason the author has decided to mention it here itself. I mean, of course, since P by definition is finite, it will have a natural number as its cardinality. Then the requirements are bare minimum. There is an interval and there is a partition of the interval. That's it. Then the length of the interval is equal to the sum of the lengths of the subintervals in the partition. It seems very natural, it should be true, and it is true. So we will start the next analysis video, next Sunday, with the proof of this, and then we will see what comes after that. So that's just it for tonight. Let me end the video here itself. And tomorrow we have number theory again, but tomorrow we don't have a video because we have already completed the first section on congruences, and now we have to solve the exercise problems. There are many. Okay, so see you tomorrow. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.